Okay, thank you very much. And Heather and Angie, thank you very much for inviting me to talk about the soil health issues. I got quite a bit of topics to cover, so I'm just going to start right now. If we look at soil health, a comprehensive soil health approach would include chemical, physical, and biological soil properties. But today, I'm going to focus on some of the key soil health issues of which I have observed in roughly 8.5 years of my work out of Langdon that I believe that are basically creating major economic losses. So here is the list. And number one, I mostly won't talk about loss of topsoil and how can we increase the soil organic matter, because when we remediate salinity and sodicity, that will take care of those issues. But if we look at the loss of topsoil, that has been huge. One study which NDSU did 5-6 years ago recorded a loss of 9 to 17 inches of topsoil in the last 50 odd years. That is a huge loss, and we are not going to see that topsoil back in our lifetimes. Organic matters also are slowly but surely, those levels are going down. I believe that we are blessed with one of the best soils in the world here. And but if we compare the organic matter levels, which when people started farming these soils, they were much higher. So we not only need to maintain them, but we need to try to increase them. And then soil salinity, sodicity, and high magnesium levels compared to calcium and an excess soil water. Like I said, I'm going to mostly be focusing on issues like salinity, sodicity, excess soil water, and high magnesium levels. I just want to quickly mention the background of these issues. These are not new issues. So this is a picture of an NDSU extension publication, which actually was given to me by an NDSU extension county agent, I think 4 or 5 years ago. And he was a county agent for 40 years. This publication was first printed in early 1960s, and it was reprinted in 67, and that's the copy I had. That publication talked about 1 million acres affected by salinity and 2 million acres affected by sodicity. So both of these issues were talked about in 1960s. So we're not talking about something new here. The recent citation, there was one recent study, I shouldn't say recent, but that's the most recent we have, in 2010, estimated that about 6 million acres were affected by salinity alone. That's about 15% of the total cropland in North Dakota, which is 39 million acres. And then most of the common salts in North Dakota are sulfate-based salts, and soils of northern Red River Valley, which will include the Minnesota Part 2, have chloride-based salts mostly. And coarse soils, we don't have a lot of coarse soils, especially in the valley, but we do have pockets where there are more sandier soils or slightly more coarse textured soils. They tend to have higher levels of sodium carbonate salts. A lot of people discard sodicity. More people are getting aware, but if you look at the soil sodicity, we have 330 soil series in North Dakota, and 42 are known to have sodicity issue. They are labeled for that according to Web Soil Survey. Now, 42 could be a smaller number if we look at 330, but those 42 soil series account for close to 5 million acres. And there are many more soil series which may or may not have high sodium levels. And I want to quickly touch on high magnesium levels compared to calcium. And I want to clarify, I'm not talking about a ratio of calcium versus magnesium from fertility point of view. I'm talking from the point of view of soil particle aggregation, and then which could lead to crusting or compaction too. Soil structure that will affect the porous space and soil water movement, air to water ratio. So that's the point of view I'm talking about. So In 2017, I myself was not aware of this issue. I was helping a producer with soil sampling, and we came across a site which had high salt levels. It had all the symptoms of sodicity, which creates dense soil layers, crusting, ponding of soil water at the surface, but it didn't have high sodicity levels. That's when we realized that there was a high magnesium issue compared to calcium. And I contacted one of the faculty members in Fargo, and he sent me some publication. One was Canadian, one was US. And you could see these are old publications, 1935, 1936. And at that time, I mention these, you could read these publications. I would be more than glad to email these publications to Heather and Angie too. If somebody is more interested in reading those, then you would read them. You would realize that they talked about soils having all the symptoms of sodicity, but they didn't have sodicity issue. They had high magnesium levels compared to calcium. So we talked about the background and the history. So here we are. For example, if you're a producer, just like the one in the picture, you have beautiful wheat crop growing on the other side. If you look at this patch where producer was standing, there was either kochia growing, very good growth, or there was nothing growing. And you could see in this picture, there was wheat seed germinated, but the seedlings died. So when you have these kind of spots, you wonder, okay, and there's not even visible white salt crust at the surface. So then we wonder, is this salinity? Is this sodicity, or is it both? So I took some sample. I helped that producer on that day, taking 3 soil sample. One was from this field. And if you just focus on 2 numbers, one would be EC, or electrical conductivity, which will tell us about the water soluble salts. This number, saturated paste test, if this is about 1.5 or 2, it will start affecting sensitive crops like soybeans. About 5.5 or 6, it will even affect the yields of the most salt tolerant annual crops like barley and oats. You look at the lowest EC level in the first 12 inches, because that's where we plant the seed, is 7.3. So definitely all sites were saline. Now we'll look at the SAR test, or sodium adsorption ratio. It tells us about the sodicity issue. If this number is 5 or more, the shrinking and expanding type of clays, which we have mostly in the Red River Valley, as well as other parts of Minnesota and North Dakota, soils will start having dispersion or breakdown of soil aggregates, which makes the soil layers dense. Well, the lowest number I have there is 16.44. That means definitely that site was saline as well as sodic. What about this site? Somebody commented that, was I ice fishing? And whatever is blowing in that first picture on the left-hand side are salts. It's not snow. So if you see that much visible white salt crust, the first thing you will think about is salinity. But was that only salinity issue? And you could see at that time I used to sample 4 feet deep with handheld auger. And we took sample, and here are the results. Look at EC. Now EC is high in the first 12 inches, but I wouldn't say EC is the main issue, or salinity is the main issue here. It's the sodicity, which is represented by the SAR test. 24 in the first 12 inches. So if I have to reverse the terms, because always in the scientific world, when we explain these 2 issues, we say this soil is saline sodic. I have come across a lot of sample results where I want to say it's a sodic saline soil. And this is exactly what I would like to use that term for this sample. So just to differentiate sodicity and salinity from each other, because they're often confused with each other, they're often mixed with each other, and we don't see the clear visual symptoms of sodicity. So often we say it would also be a salt issue. Actually, it is not. If we look at the salinity issue, that is a excess water soluble salts issue. Salts are a combination of chemical ions, for example, table salt, sodium plus chloride. They attract each other with their negative and positive charges. Sodium, which causes sodicity, is attracted to soil particles like clay and humus. Sand and silt doesn't have any charges. As long as sodium is present as a salt, it will not cause sodicity. It is true, though, that if we have lots of sodium-based salts in the soil water, more sodium will ultimately get attracted by the negative charges of soil particle. It'll go to the exchange sites and it will lead to sodicity. But as long as sodium is present as a salt, it will not cause sodicity. The most common negative effect of salinity is that salts compete with plant roots for water. They deprive plant roots of water even under decent moisture conditions. So on the left-hand side, we have a green, healthy growing plant. And they're not, the salts are represented by the white dots. So plants are able to take up the water in their cells because it is not enough pull by the salts into the soil. On the right-hand side, there are lots of salts in the soil water, and plant roots will still try to pull the water molecules into their cells, but the pull is more stronger in the soil to keep the water in the soil, not to let the plant roots take it up. And the result is drought stressed plants. So salinity affects plants directly, but it doesn't affect soil per se, or soil structure, or soil particle aggregation. In fact, if we have more calcium-based salts, calcium ions, because of their two positive charges, can act like a bridge, so lead to aggregation of soil particle, which is called chemical aggregation. And then because of their smaller hydrated ionic size, they don't also let a lot of water seep through clay layers. So clay layers will not expand or shrink the way, for example, other chemical ions can do. Excess sodium leading to sodicity when it forms combinations like sodium plus clay, sodium plus humus. It breaks those clay and humus particles away from the larger aggregates. So the aggregate size will keep getting smaller and smaller. Soil layers are going to get dense. Soil pores are going to get plugged. And this is what I consider chemical compaction. The mechanical compaction is a result of equipment, traffic. This is what I consider chemical compaction. We talk often a lot about compaction. This is what can happen. And a lot of people say we have clay soil, so we will have slow water infiltration. Yes, a clay soil will have slow soil water infiltration compared to sandier or silty textured soil, but a clay without this problem, this dispersion, will have much more faster soil water infiltration compared to clay with dispersion issues. So I'm going to provide you with a very crude example. These are two jars. I stole some wheat from my research station, and I stole two of my wife's canning jars. One has wheat, and so wheat kernels, I wanted to represent them as like soil aggregates. So if you look at them, these nice sized kernels, they have very decent pore space around them. And if you pour the water in this jar, it will go very fast to the bottom. On the other hand, we just grinded the wheat. So you see we reduced the not soil, but the wheat kernel particles to a very smaller size. So the layers of flour are very dense compared to kernel layers. Pore space is shrunk. So if I pour the water on the jar on the right hand side, it'll take for the water a long time to get to the bottom. And I want to use this picture or diagram, even though magnesium is not here, to explain what high magnesium levels compared to calcium can do to soils. So for example, sodium, it has one positive charge. It cannot act like a bridge to promote soil particle aggregation, and it has a very big hydrated ionic size compared to say calcium. So it lets a lot of water seeps through between the clay layers, and that leads to swelling of the soils. And the result would be the same like dispersion. It will reduce the soil pore space. Now, magnesium has two positive charges like calcium, so it can also lead or promote aggregation of soil particles, but its hydrated ionic size is bigger than calcium. So in shrinking and expanding type of soils, it could actually lead to more swelling. if the concentrations of magnesium ions are more than calcium. So I'm just going to go back to the same picture. So for example, if we pour the water in the left-hand jar with wheat kernels first time, the water will move down faster. But if we let the water sit there, wheat kernels are going to swell. And once they're going to swell, and if I poured the water again for the second time, now because of the swelling of the wheat kernels, water will not move faster through the pores because the pore size will shrink. And that's what magnesium can do to soils. So the ultimate bottom line is whether it's dispersion or swelling, it will slow down soil water infiltration. Here are the two results I was talking about when I first got aware of the high magnesium levels compared to calcium. So I was helping this producer with sampling 2 sites which had similar symptoms, few miles apart, actually in the Red River Valley. It's in Pembina County, slightly east of Mountain. If you look at the results, both sites have salt issues. The saturate paste EC on the left-hand side is 6.84, right-hand side 6.09. The difference is on the right-hand side, SAR is 10.63, a typical case of saline sodic site. On the left-hand side, sorry if I said left-hand side for the high SAR, it's the right-hand side result, 10.63. The left side result had a SAR of 2.89. That means the site was not sodic, but it had the same issues of ponding of water at the surface, very slow soil water infiltration. So then I started looking a little bit deeper. And if you look at the magnesium levels, that is 74.14 compared to calcium of 25.27. And that's when I contacted other people in Fargo and I got those publications, and I came across these reports that this issue is common in Red River Valley. So I haven't done much work in Minnesota, but I'm pretty sure soils are quite similar, especially Pembina County, which borders Minnesota. Here's a result of a soil which doesn't have any salt issues, doesn't have any sodicity issues, and doesn't have any high magnesium issues compared to calcium. EC, even in the 6 to 24 inch depth, is slightly over half millimoles per centimeter. So we could plant any crop here, even beans or anything. SAR is not calculated here, but SAR basically uses, the formula uses calcium to magnesium and sodium numbers. If you look at the ratio of calcium for each sample, it's either 2 to 3 times more than magnesium and even more than sodium. And that's exactly what we want to see for good soil particle aggregation and not leading to dispersion or swelling. Our soils will swell in the Red River Valley. We have shrinking and expanding type of soil, but you don't want to add to that. I want to also quickly touch how these saline sodic areas are formed, especially along the headlands. So this Google Earth picture is of a headland or area which is 4 or 5 miles east of Langdon along Highway 5. If you look at that, there's a natural drop from south to north about 17 feet, I think. 1665 is the elevation on the south side and 1648 on the north side. So if you think about the time when there were no roads, the water would have naturally drained from south to north. Humans came along. I love roads. I love cars, actually. My wife always complains about that because I'm always looking at the car, whether we can afford them or no. So I like paved roads. I like highways. But when we built these roads, we compacted, we disrupted that natural drainage of excess water going from one point to the other. And then we dug up the sides of the roads to make ditches to make the highways higher. So what's happening now? Water is going to that ditch, and ditches doesn't flow well either. And it just sits there and acts like, it's like a pond. And then vicks back to the higher productive ground, and it That's why we most of the time see these saline sodic spots developing around headlands in field ditches. Another picture, you could see that white area there. Now, in this picture, there's a 3 feet drop from north to south. Same thing, same concept. This picture, by the way, is a close-up of the first Google Earth picture I showed you. So if you look at that, there's slope actually. So when it rains, and this picture I took in 2017, which was quite dry, but I just took it right after a rain. Higher productive ground, when it rains, excess water came to the ditch. It cannot go on the other side of the highway, even though there's a drop. The ditch doesn't flow good. So free gravitational water moves from higher to lower elevation. That's what it did. But then the capillary water, it could vic up in any direction from the forces which move it are adhesion and cohesion from wet to dry area. So higher ground got drier, headland is still wet. When the higher ground got drier, headland water started vicking from the headland into the higher ground, and it brings salts with it. So there comes a time when salt levels are so high that crops cannot grow, and that's why these rings of salty areas keep getting bigger and bigger unless we do something different about them. Just quickly, gravitational water is the free water. It's not plant available water. It moves from lower to higher to lower elevation. Under poor drainage, it could actually cause shallow groundwater depths, and that's what happened during the wet cycle. Under good drainage, it actually can move the salts and contaminants into the deeper depths. And this is the water which is going to take care of your salts. Capillary water, on the other hand, can move in any direction from wet to dry area, and it moves due to the forces of adhesion and cohesion. Adhesion is the attraction of water molecules for soil particles, and cohesion is the attraction of water molecules for each other. This actually can cause bigger issues under the drier weather. For example, if we wanted to leach our salts, say 4 feet depth, our water table is 4 feet deep. But if we're going through dry weather, there would be not enough water to force the salts into deeper depths, but there would be more water will just start vicking up towards the topsoil. And just to give you a perspective, not that in every soil this is going to happen, but because of the forces of adhesion are the forces that means that water molecules are attracting soil particles, and sand and silt doesn't have any negative charges. So in clay soils, heavy clay soils, this capillary rise could be as high as 8 feet. And we have mostly clay soils. And I'm not trying to say that in every soil this is going to happen, but I just wanted to quickly show you this diagram or picture. Coming back to that headland. So this is the same headland which I showed you in the first Google Earth picture. I took this picture on May 3rd. You look at the headland, it's not suitable for any annual crop, in my opinion, but the farmer went ahead and planted one, canola. And if you look at the picture, that's a net loss. Basically lost everything, whatever he spent on fertilizer, seed, and fuel. And here are some NDSU numbers. So these are NDSU projected 2020 crop budgets for Northeast North Dakota, but I'm pretty sure they would be also relevant to the producers in Minnesota. What I did, I just took the cost of the seed, fertilizer, and 1/3. I divided the total cost of fuel and lubrication by 3. And here are the numbers. So it cost about $100 to plant 1 acre of a spring wheat, 140 ones for canola. Corn cost us about $171 per acre, soybeans $81. And if you look at this picture, we have lost money. That's a total loss. I want to also quickly touch about tiling, because tiling sometimes is presented as one-step solution to take care of all the problems. So tiling will work if we have excess soil water and we have good soil water infiltration. That way, tile will lower the groundwater depths. There's enough rainwater to force or push the salts into the deeper depths, and we have good soil water infiltration. So in this picture, tiling depth is 4 feet deep. So the layers, 4 feet layers of soil, if they do not infiltrate water in a timely way, we are not going to get good drainage despite tiling. And that's exactly what sodicity or high magnesium levels can do to these soil layers, slow down the water, soil water infiltration. And I think we don't talk enough about soil water infiltration. And it's not just the amendments which will improve soil water infiltration, it's the no-till and other measures too. This is a tile demo site slightly west of Admore. And there was a demonstration. They put in some tiles from the headland about 125 feet into the field. And if you look towards the trees, that's east up until there is a fourth electric pole. It was tiled in 2011 or 10, even before I joined NDSU, and the site had a little bit of salt issues. Nobody tested it for Sodicity, by the way, and in my view, that's a mistake. When you have a problem area, get it tested for everything to rule out any other issues. Anyway, site kept getting worse. And mind you, these were wet years. There was plenty of water. Site was tiled, but it kept getting worse. So what was the issue? We finally found out it was a sodicity issue, and the site kept getting worse. This is 13. This is 14. This is 15. We tried different cover crops, this and that, nothing worked. In 14, though, October, what we did on east side, center, and west on small plots, we applied beet lime, gypsum, elemental sulfur, and one plot we left as is as control. In between, we left the areas as is. We didn't do anything, only because we couldn't afford to do a big trial. 3 or 4 years later, a farmer during that time just kept planting annual crops, and he was losing money, but he was doing it. But 3 or 4 years later, whenever I would drive the car on this highway, which is 17, and county agent would drive, he would say, okay, those spots now started showing some positive results. And it started supporting crops. And actually last year, those spots actually grew very good crop. But the areas in between where we didn't do anything were still bare. So what we did ended up applying amendments on the whole spots. And here are some soil results to compare. So like I said, east, center, and west, we distributed this whole strip into these 3 areas. And if you just look at the EC and SCR values of both soil depths and compare them with the results of 13 versus 15, on the east side, EC levels doubled in 15 compared to 13. SCR actually went 3-4 times higher. West side was not as bad like east, but worse than center to begin with. So EC levels again went higher 2-3 times, but it was the SAR which went 3 times up. Center, there was not a lot of change there because it didn't really have big issues. What I want to try to say by showing you these numbers, that one concept is that if we tile the site, which is high levels of salts or moderate, and then moderate levels of sodicity, when you tile, with tile in place, salts will leach out first because they're water-soluble salts. Sodium is attracted to those soil particle negative charges. It's not really mobile in the soil water. And that could actually make the sodicity issue worse. And this is exactly what happened here. So number 1 step for managing these issues is to take a soil sample. I cannot really emphasize more on this. So this is the number 1 step in my view. When you see a problem spot, looks doesn't tell you everything. So you take a soil sample, you get it tested for electrical conductivity or EC, then sodium absorption ratio or sodicity and pH through saturated paste extract method. So I'm stressing upon the method. It's not just the test, but the methods. And zone sampling is better. Why we want to go 3-4 feet deep instead of 0 to 6, 6 to 24? Because most of the plant nutrients are in the upper 6 inches. That's not the case with salts and the sodium or the magnesium. And then we want to get each depth analyzed separately for these tests. If we have a need for amendments, and we don't need amendments for salts, we only need them if we have higher sodium levels compared to calcium, which will lead to sodicity, or higher magnesium levels compared to calcium. Then we need to analyze first foot for cation exchange capacity, or CEC, by using sodium saturation method. You could also get this number through web soil survey. Label each sample clearly and communicate to the lab what test you want through what methods. Lab wouldn't know. Otherwise, they're just going to use the run-of-the-mill common, I should say, methods. And here's why I was emphasizing on methods and why it's important. So if you just look at the CEC numbers, the common method is summation or addition, and it gives you artificially high CEC, especially if we have high levels of water-soluble salts, which in this case it was. So CEC through summation or addition method is 50.6. CEC through sodium saturation is 16.8. So you see the difference, 3 times more CEC through summation or addition method. If we look at this water-soluble salt results, the common method is 1:1, 3.43. Saturated paste method, 6.5. If you ask me what should I plant at 3.43, if I don't know what method was used, I would say maybe barley or oats. But if I look at 6.5, I would say no, perennial grasses, because you won't even profit from barley and oat crops. And how does these affect our bottom line? So for example, I took all of these numbers from the previous test. So the SAR was 10.71 if you want to look at it. So say, for example, there's need for amendments. We want to bring that 10.71 to 5. So I deducted 5 from SAR initial, and SAR final is 5.71. USDA formula uses exchangeable sodium percent, or ESP, so I converted it into that. Now I'm going to use 2 different CEC numbers, which are from the previous test. So the summation or addition method number 50.6 gave us the recommendation of 5.75 tons of 100% pure gypsum per acre. The other, which is called true CEC, is 16.8. That gave us a recommendation of 1.91 tons of 100% pure gypsum per ton. So roughly, if you look at them, if the CEC was 3 times higher, the gypsum recommendation went 3 times higher, even if we kept the sodicity levels the same. And just to give you a perspective how much it costs, the cost difference between these 2 tests, NDSU Soil Lab charges $15 to analyze samples for CEC through summation or addition method. And for the sodium saturation method, it charges $25. So there's a difference of $10 per acre. If you pay more in the beginning, you'll save much more later. So if we look at the steps to remediate salinity, number 1 thing is to lower the groundwater depth. If there's a low area which is always full of water, or groundwater depth is very shallow, we are not going to get rid of salts or sodium or magnesium issues. Because say if the groundwater depth is 1.5 feet below the surface, the water will move the salts or other contaminants to that depth, and it'll just sit there and wick back, whether it's surface drainage or subsurface drainage. Second thing, we cannot control the rain, but what we could do is to reduce evaporation, because less evaporation will mean there's more moisture in the topsoil, so there would be less wicking up of soil water or the capillary water from the ground to down there to the topsoil, and that would mean less salts coming into the topsoil. And we also need rain. We realize, I also used to think you lower the groundwater depths and salts are going to go away. Yes, under decent rain events. And what I mean by that is not just the quantity, but the timing as well. So for example, if we got 2 inches of rainfall in 2 hours, most of the water is going to run off. It's not going to go into the soil to leach those salts into the deeper depths. But if our soils are dry, and if you got 100 or 200, that's not going to move the salts either. We need soils at field capacity or even a little bit drier and at least 1/2 inch or more. Plants will take up some water, soils will hold some water, and then there would be some in a free gravitational water, which will force the salts into the deeper depths. So bottom line is, if there is a smaller gap between evapotranspiration and actual rain, there would be more leaching and less wicking up. I'll give you a quick example. In 2016, our weather station here recorded about 25 inches of rain, and our evapotranspiration was close to 35 inches. So 10 inches of gap. We reduced EC levels from say 8 to 3.5 or 4 that year. There was enough water, site was tiled. Come 17, the actual rain was 10.25 inches, and the evapotranspiration was still 33, 34 inches. So the gap increased from 10 inches to 23. Now the salt levels didn't go back to 2014 levels, but they increased more than 16. So say they went back to 5 or 6. I also want to quickly show you a few pictures of a trial we had in 2020. So often we get the question, what are the most salt tolerant annual crops? Barley, oats, and sugar beets could be your best bet on problem areas with high salt and sodicity levels. So what we did, we planted 4 barley varieties, 4 oat varieties at our research center at 3 different levels of salinity and sodicity. So this was low to moderate levels of salinity and sodicities. EC in the first 6 inches was 3.99 millimoles per centimeter, and SAR was 7.12. That EC is not really low for crops like soybean, but for barley and oats, you could see how they are growing. And I could tell you, even when I was tilling the soil, yes, I'm a soil health specialist. I'm telling you I tilled the soil because my research agronomist wanted that. So I did that, and the soil was working like garden. And this is how barley and oats are growing. And our highest barley yield in this treatment was about 101 bushels per acre, and oats highest yield was 121 bushels per acre, or 123. I don't exactly remember. Here is our moderate to high salinity and sodicity level treatment. So here, surface salinity, EC, in the first 6 inches went from 4 to 7.5 or something, and SAR increased from 7.12 to 14 point something. That made a huge difference. And I actually pulled some roots from the good as well as this second treatment just to see what is the rooting depth. And I realized that in the first treatment, in the 6 to 24 inches, EC was actually high, but the plants were adapting by keeping their roots shallow in the first 6 inches to survive. Plants try to survive if they get a chance. What happened here was that even in the 6 inches, the EC levels were too high for these plants, and this is the result. And when we came to the very high levels of salinity and sodicity, all 4 barley varieties didn't even germinate until the end. Oats, this is one thing we learned, that oats actually, tolerated more salts than even barley. ND heart, actually, there was a little bit of germination in all oats plots, way later though, compared to other treatments, but ND heart yielded 5 bushels per acre, which is very low, but on these kind of spots, something is better than nothing. So what should we do when we have these kind of spots? Very high. We cannot plant anything annual. And here's another example. So this is a retiling project site, a long-term research site. We tiled it in July of 2014. I took this picture in the spring of 2015. And we applied the amendments in July and August. So then I said, what should I plant here? I got to plant something here. I'm not going to leave it like that. So I went and the mix I most commonly use, I planted a mix of 5 salt-tolerant perennial grasses here in September 2015. And this is how the site looked in 16. So there are options available, even for the worst possible spot, if we keep our mind open. Here's a farmer example. Slightly west of Langdon, this producer planted a salt-tolerant alfalfa on 3 acres. He has some cows, nothing germinated. He contacted the local NRCS office, and we all went together. We took samples. He replanted the same perennial salt-tolerant grass mix with some alfalfa in it. And this is how it looked in 2017. I want you to notice that grasses are growing everywhere, but alfalfa is not really growing everywhere. The growth is spotty. So here's my thinking is that alfalfa seed remain dormant. Grasses take about 1 year to get established, and they could tolerate more salts. They reduced evaporation, then roots went deeper. They created channels for the rainwater to move into the soil, leach the salts to a deeper depth, and when alfalfa seed found the opportunity, it started germinating and getting established. So on these spots, we feel that by taking a gamble of adding 1 or 2 pounds of cheap alfalfa seed with grasses can pay a lot in the long run because it could increase the quality of the hay. So I took some samples in 12, 14, and 17, and I just want to quickly tell you, if you just look at the first 6-inch results of EC and SAR, where there was no alfalfa versus there was good alfalfa. So wherever the EC levels were at most 1.9 millimoles per centimeter, or decisiemens per meter, or 2, alfalfa was doing good. But as soon as the EC levels got to 5, alfalfa didn't even germinate. It wasn't there. Same thing goes for SAR. The highest SAR was about 1.47, where alfalfa is doing good. And where it wasn't doing any good, the lowest SAR was 5.5. So this producer, he replanted these grasses along with alfalfa. Grasses took about 1 year to get established. Alfalfa took 3 years. In 14, he got 3 hay bales out of 3 acres, roughly 1,200 pounds each. 15, 4 hay bales. 16, 5. 17 and 18 were very dry, so he got 5 hay bales in each year. I don't have the data from 2019, but here's how his spring wheat looked last year. Last year, he tore it up and he put it back into an annual crop, and this is how it looked. And I just want to quickly tell you that the trial, which we incidentally learned that these grasses nurture alfalfa, again happened at the research station. We planted this strip in 2015. We just added 1 pound of winter hardy alfalfa variety in this. It took 3 years for alfalfa to start getting established. Grasses took about 1 year because they're perennial. But for 3 years, we didn't even see any alfalfa plant. But this is how it looked in 18. This is how it looked in 19. This is how it looked last year. So this is something we are learning by accident. I'm not going to claim any credit for that we on purpose. Yes, we added the seed on purpose. We just said, let's just try this. But we learned this. And I also want to confess that we also at the research center used to plant annual crops where there would be nothing growing there, and then people would go and till it up because they didn't like the white look, and we were losing money. So in 2014, 15 acres were planted with a grass mix without alfalfa, and in 15 we had it. A local person had it, and he got about 30 hay bales, so 2 hay bales per acre, each one weighing roughly about 1,500 pounds. And since then, sometimes some ranchers, if they are short on hay, they have hayed it, but I don't have the data. Otherwise, we just mow them. So here's the bottom line. On these problem areas where we cannot plant annual crops, we could still profit. We could still profit. And here's quick comparison. So I use the same NDSU crop budgets I showed you in the beginning. And for example, in 4 years, we planted canola, spring wheat, soybean, and corn. Using those numbers, we spent about $494 in 4 years per acre, which was a net loss. And then if instead of doing that, if we planted on another acre similar grasses with 1 pound of alfalfa seed, we planted that. And then in the second year, it takes grasses about 2 years to suppress the weeds on their own. And this is exactly the herbicide mix we used on our trial site. You could still control the weeds if you don't like them through herbicides, $14. And I want to emphasize that we need to cut these grasses, whether we want to mow them, hay them, or graze them, because when we cut the top, the roots go deeper, and that's when you see the benefits. So say, for example, even if you are not haying it, even if you're not grazing it, grazing to me is the best, more than even haying. And in a year, depending upon the rain, you will have to probably mow the grasses 3 to 4 times. So $10 per acre per mowing. Your cost at most in 4 years would be $140. If you deduct $140 out of $494, you're going to save about $355. Plus, that's going to help the land. It's just pure numbers. So coming back, how should we manage these headlands or these saline sodic spots? So this is, again, this headland is the picture I showed you, the Google Earth, the second one example. So if you have a headland like that, just going by the look, I would say that no annual crop will survive here. So what I would do, I would plant the perennial salt tolerant grass mix with about a pound of alfalfa in it. How wide you should plant initially? Initially, I may just want to plant the whole wide area because no annual crop will survive there. But when higher productive ground will start improving, then I would narrow it to about 30 feet wide. And what those grasses will do, some of the grasses in that mix can establish roots 5-6 feet deep in 3 to 5 years if we cut them, mow them, hay them, or graze them. So say if that grass mix is growing there, excess water drained from higher productive ground to this headland, and when it would start wicking up from headland to the higher productive ground, those grass roots can intercept that water. That is capillary water, which is not intercepted by tile lines, but plant roots can do that. And here's that mix, which I have been using very successfully. I would highly recommend it. Tall wheatgrass, slender wheatgrass, western wheatgrass, green wheatgrass, or AC Saltlander, which stands for Agriculture Canada. Very good grass, but it's a mix of bunch and quickgrass. So if you're planting this mix close to a native pasture and you cannot spray Roundup, for example, then discard this mix from the discard this grass from the mix because it could be a problem for you. Otherwise, it's very good. Russian wild rice. Seeding rate for all 5 grasses per acre, I would say 8 pounds should be sufficient. Depending upon the prices, sometimes it may cost you $35 per acre. It could cost you $40. It's a one-time cost. And grasses take about 1 year to get established, 2 years to suppress the weeds. Now, if we have sodicity, so we talked about salinity, which doesn't require application of any amendments. Because these are water-soluble salts, we need to improve the drainage, lower the groundwater depths, and pray for more rain. We don't want too much rain, but we don't want too little either. So if we have a sodicity, which will happen if we have higher sodium levels compared to calcium, that means now we'll have to add calcium through amendments, which could be gypsum, it could be beet lime or commercial lime, it could be other things too, but I'm just going to use gypsum as an example. So gypsum is calcium sulfate. When we spread it, we have to incorporate it so that it could be in contact with the soil particle. Then the calcium will separate from sulfate with the help of water. That means rain again is going to play a role here. Displace that sodium from soil particle negative charges. Sodium will come into the soil water, and that's where it's going to convert into a salt by attracting a negatively charged ion. So by applying amendments, first we'll convert sodicity into salinity. And that's why we need to still follow the salinity remediation practices. Same principle will apply to the high magnesium levels compared to calcium. Some people say it's not a problem. I personally have a different opinion. Yes, it may not cause dispersion, but it still can cause swelling. And the bottom line is that will shrink the pore size. And again, this problem will happen if we have higher magnesium levels compared to calcium. So then when you apply, say again, gypsum, calcium will separate from sulfate, displace magnesium from soil particle exchange site. Magnesium will come into soil water, convert into a salt. And again, we'll have to follow the salinity remediation practices. And this is my last, sorry,
Okay.
go ahead. Yeah.
I was just gonna say it's 10 minutes to 9. So.
Okay, last slide. We've observed that tiling did not lower salinity under drier weather. So that's That's people should understand. Yes, under decent water, it could. Sodicity didn't change. And I'm talking about the results of a trial, um, which is 6 years old. It's been tiled for 6 years. We applied the amendments 5 years ago. Also, we learned we take water samples from the water which is draining from the tiling project site into a surface ditch, and then we compared from upstream and downstreams. We have about 10 sets of sample, and in all 10 sets of samples in 5 years, this water, tile drainage water, is adding salts, sodicity, lime, nitrate, nitrogen, selenium to the surface water ditch. So people who are considering tiling, I just want to tell them that even if your tile drainage is working properly, you should also consider what that water is going to do to the neighboring fields and the quality of the surface water resources. So with that, that was my last slide, Heather. Thank you for giving me extra time. You're muted, I think.
If the attendees, you have questions, please put it in the Q&A box for Naeem. Thank you, Naeem, for joining us today. And we will hear a little bit more from you, just a quick recap next week before we get started into the next portion. So thank you for your willingness to help and participate with us too. So attendees also, if you, go ahead, Angie.
I have some questions as well here.
Okay, go ahead.
Okay, so in the meantime, feel free to add your questions into the Q&A, and if we don't get to them, we can make sure to pass those along to Naeem Kalwar and get them answered for you. First of all, thank you for admitting that the Langdon Research Center also tried to crop those problematic acres for years. I think that a lot of times it's really hard to make a change. One question is, do the winds in the Red River Valley and our lack of shelter belts have any effect on saline or sodicity issues?
Yes, it has more effect on erosion, but the picture I showed you, your salts were blowing. Well, those salts were going somewhere. So that means they're going to end up at probably on a field where it probably didn't have high salt levels. So that doesn't happen very often. Mostly it just blows the topsoil, especially if we till it, you know. But yes, salts can also blow. I've actually seen clouds of salts at one time. I was just driving the car, so I couldn't park it and take the picture. It would have been a very cool picture. It was just like a snowstorm. So yes, wind can play a huge role.
We have an attendee that asks, is the seed mixture of perennial grasses that you are using available from NDSU or extension offices, or where do you get that mix, or do people need to make the mix on their own?
It's available through private companies so far. I would tell you that I convinced my boss into planting about an acre of these grasses. In my point of view was at that time that these acres are not producing anything. Why not produce seed for this? And I would actually tell this to all the young and old farmers. This could be a business for you, because these private companies are buying this seed from Washington Estate and other estates far away from us. They're not really adapted to the weather conditions here. In some of these your problem areas, if you planted them, if you have a way of sorting the seed, you could actually make a business out of it. So far, I would just tell you there are 3 companies in North Dakota. Reward Seeds, actually they are based out of East Grand Forks. Agassiz Seeds based out of Fargo, and Pulse USA based out of Bismarck. And I would always shop for pricing, for best pricing. They change. And so far, we also buy seed from them, but we have planted these 5 acres last fall. In about, I think, a year or two, I'll try to convince my boss whether he wants to sell it to the companies or directly. We sell foundation seed, actually. So I would try to convince him to sell it to producers. You know, One variety we cannot sell, AC Saltlander, because of the patents and the rights, but the other 4 we could. I personally would just convince him to give that variety for free to producers. If we cannot sell it, just give it to them, So we are trying this. This was not in my mind when I started this, but then I'm thinking, why not help these people? So.
Great, thank you for that. So one thing that I've heard a lot since coming to the Red River Valley is that our compaction issues are, we don't really necessarily have to worry about our compaction issues because they're fixed by our freeze-thaw cycles. 1, is this correct? And 2, how does chemical versus physical compaction affect remediation when relying solely on freeze and thaw?
So Dr. Dave Frenson is of the view that the shrinking and expanding type of clays are very forgiving after a rain or so. But then if you talk to Aaron Day, he says no, freezing and thawing is not enough. I would say that, okay, yes, freezing and thawing will take care of these issues to a certain level, but why should we add to the problem? So we should try to minimize the traffic wherever we could. But the chemical compaction I talked about, to me, this is just a term I came up with. If you want to try to find a publication, you may not find it. But I personally think that it's the same thing. It just makes the soil layer dense. What else I should call it? So it's related to traffic as well as related to the chemical compaction. I don't think that the physical freezing and thawing cycle will take care of the chemical part, because chemical compaction or dense soil layers or dispersion or swelling is happening because of the soil chemistry. It will still crack, but in between, the layers will still be very dense. It's like when people tile, wherever the tiling plow goes, they get a very good crop. But in between is still nothing grows. So we've got to take care of the whole area in order to have a uniform stand and make a profit.
Do you have time for one more question or?
Yep.
Okay, great. So the last question is, what happens when someone adds gypsum, let's say, when their problem isn't really a sodicity issue? Is there any kind of penalty besides the cost of the product itself?
I'm not aware that high calcium levels can cause any issues. But I would say that, just to give a perspective, there are roughly 2 million pounds of soil in the 6 inches in 1 acre. So even when we apply 10 tons, that's 20,000 pounds. It's a drop in the bucket. So I wouldn't say there is necessarily a negative effect apart from the financial aspect. So for example, if your soil calcium levels are 2,000, whatever the unit is, and magnesium is 600-700 and sodium is 200-300, that's kind of like a useless exercise. Gypsum could cost you, depending upon the source and transportation costs, from $40-50 to $350 per ton. So I mentioned in my presentation, I like cars. So when I go, I just see, do I need that? Do we need to spend money on this? So I would say that if we talk about profitability, why should farmers spend money on something they don't need?